Okay, good morning, everyone. Here we are yet again, another inclement weather day. So please check D2L for the updates. So this lesson is going to be on our hydrocarbons section of the textbook. So this is the second lesson in your organic chem note package. So please follow along as we go through, and there's examples that you're going to kind of try out along the way. Okay, so essentially, as I mentioned, organic compounds have carbon as a backbone in all of their molecules. So a hydrocarbon kind of makes sense with the name, right? So a hydrocarbon is something that has carbon and hydrogen in the molecule structure. Now you can have additional different types of elements, like different functional groups that we looked at the other day, but today we're focusing on, like, this lesson is just solely going to be carbons and hydrogens. Okay, so there's two kind of formats that they can come in, aliphatic and aromatic. So aliphatic really means chains of carbons. So if I were to flip to this for a second here, so it would be, let's say, oof, this is gonna be rough with the mic, with the mouse here. So anytime, so from now on, actually this entire unit, whenever I put a tick, like a dash line coming off of the carbon, you are assuming that those are hydrogens. Okay, it's going to start getting really complex. Like you can have 10, 12, 14 different carbons in a structure. To write in all of those hydrogens, it gets very confusing and time consuming. So I always do these tick lines. So just assume those are all hydrogens. So this is an example of something that's aliphatic. So meaning it's not like a circle. So for example, let's say I had three carbons, three carbons kind of combined in a circle formation or a cyclic form. So here I have three carbons that are kind of interconnected. This is considered to be a cyclo group. Cyclo. Okay. So a cyclic group is technically also a type of aliphatic molecule. What makes something not aliphatic is actually if it's considered to be aromatic. So just going back to this one for a second. So aliphatic is where you have carbons and hydrogens and they're combining in some sort of way. They can be straight chains, they can have branches, they can be in a cyclo form. Aromatic is very unique, in which we have a benzene molecule. So a benzene is where you have six carbons and they're all interconnected with alternating double bonds, and you'll see that in a slide coming up. Okay, so aliphatic. We have three kind of general categories of how carbons can combine. So we can have carbons that are all together with single bonds only. So that's considered to be an alkane. So now the names will start to make sense to you when we look at nomenclature rules. So an alkane, which ends in ane, is representing a molecule that only has single covalent bonds between carbons. An alkene, ene as the ending, represents when we have at least one, okay, but you can have more, but at least one double bond between the carbon. So you could have five carbons, all of them single bonds except maybe one. So you have one double bond in there. It is still classified as being an alkene. Okay, then we have an alkyne. So alkyne is YNE as the ending, and that's when you have a situation with at least one or more triple bonds. Okay, so technically, if you remember from functional groups, an alkene and an alkyne is a type of functional group. So you have a multiple bond here. So you could have a situation where you have an alkene with an alkyne, so like a combination. So meaning you may have a double bond and a triple bond. Obviously, we're just learning this at the beginning here. So once we get through and we've seen some examples, you'll get more and more comfortable with seeing multiple functional groups in a molecule. Okay, so these general formulas that are down here is sort of a friendly reminder of understanding how many hydrogens have to go along with your hydrocarbon. So just use n as any whole integer. So for example, let's say we had four carbons in an alkane, right? So there'd be 4 carbons. There would have to be 2 times 4, which is 8 plus 2, so 10 hydrogens. Now, to be perfectly honest, when you draw out the structure, you know that all of the bonds are going to be filled with hydrogens. So take these general formulas as like a grain of salt, like just kind of help you, but not necessarily is going to make or break you knowing if something's going to need 10 hydrogens or 12. Like when you draw out the structure, you're going to know what you need. Okay, so aromatic hydrocarbons, as I mentioned, is where you have at least one or more of these unique structures called benzenes. So a benzene has 6 carbons and 6 hydrogens, and they do combine together to form a cyclic structure. Okay, so this is different from carbons that are just simply connected in a cyclic form. This is very unique in that they have alternating double bonds. So meaning if you take a look here, we have 6 carbons, but notice it's a double bond, single bond, double bond, single bond, double bond, single bond. Okay, there's a few ways that you can actually draw this out. So this first picture here is showing you all of the actual individual carbons. This symbol here represents the exact same thing. Okay, so this is what we call a carbon skeleton. Okay, so a carbon skeleton means that you're not actually writing out the C's. What we're doing is we use lines to represent the bonds between C's. So essentially each point on this shape represents a carbon. So this is like carbon, 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 carbon. Okay, one single line between the points represents a single bond. But you'll notice here it has a second line. So this is representing a double bond. So you'll see here single, double, single, double, single, double. Same thing. An additional way to represent a benzene ring is a different picture. Oof, okay, sorry. So this is the one that was shown before. So you have 6 carbons and you have those alternating double bonds. This is the same thing as, let's see if I can do this nice here, drawing the same shape, okay, but instead of drawing the alternating double lines, we represent it with this circle in the middle. Okay, so this is benzene. So again, so it's 6 carbons and 6 hydrogens. Okay, so when you're doing this, you can represent it with, let me go back for a second, this structure, or this structure. I'll be honest, I use this probably 99% of the time because it's just easier to do. So just to draw in the circle. Now, keep in mind, these carbon skeletons can be used for other, like not just benzene, but other compounds as well. So I'll show you what I mean by that. Let me get a new slide here. Okay, so let's say I have 1, 2, 3, 4. Okay, so let's say I have an alkane. Okay, so remember, an alkane is anything that has single carbon bonds. Okay, and I have 4 carbons in here. This, of course, remember those ticks represent hydrogens. This is the same thing as if I were to do this. Okay, so I know this seems kind of weird, but see how each point, so this is a carbon, 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 carbon. And because they're all single bonds, they have a single line between them. Now, why do they take on this kind of zigzaggy shape? It's because of actually, we're trying to represent the Vesper formation here. So each of those carbons is a tetrahedral form. So remember, keep in mind, we're not drawing in the hydrogens. It is automatically assumed that when you're looking at a carbon skeleton like this, that those carbon points are filled in with hydrogens. You never draw in the ticks when you're doing this format. Now again, at the beginning, so probably for your first couple of days, you're going to be doing your pictures looking like this, your diagrams. Over time, and as you get more comfortable, you're going to start doing these carbon skeletons just because they're way simpler, especially when you start drawing more and more complex things. Okay, so I'll give you another example. So let's say I had an alkene. Okay, so meaning I had a double bond here. I'll do the same thing, like 4 carbons, except an alkene. So remember, the hydrogens are like your fillers. So notice this carbon, I have a double bond here, so I'm only putting in 2 hydrogens. This carbon has 3 bonds full, so I'm only putting in 1 hydrogen. So if you're drawing it with writing in the C's, like the actual carbons, you must show your hydrogens. You can use tick lines. It doesn't have to be like the H's, but you have to show them somehow. So let's take this into a carbon skeleton. We would go 1, 2, 3, 4. But because I have this double bond here, I would put a double line. Okay, obviously it should be kind of parallel to that first line I drew, but so this is a 1, 2, 3, 4 carbon structure, and I can see that the first and second carbon have a double bond between them because of the second line. So carbon skeletons, way easier to draw. Don't start going into that right away. If you need, you need some practice with some other molecules first. Maybe by the middle of next week, you'll get more and more used to doing that. Okay, so going back to the lesson here. Oh, sorry. Yes, benzenes. I kind of went off to show you the carbon skeleton pictures there. So the reason why benzene is so unique, and you'll see when we spend time looking at reactions next week on different types of reactions these molecules can do. Benzenes are a very stable structure. So meaning the fact and what makes it so is not because there's double bonds. Okay, actually what it is because of the shape that it's in, this cyclic formation, the double bonds that are alternating include pi bonds. So remember, anytime you see a double bond, you have a sigma and a pi. So between each of these carbons, so each carbon here has 1 sigma for each carbon that's attached, and a pi bond between the one that it has a double bond with. So if you take a look at every single one, they're all the same. They all have 3 sigma bonds and 1 pi. So what happens here is these carbons are all sp2 hybridized. So you have to imagine these are, what we're looking at here is just the sigma bond. So this first picture, the top view, this is showing you only the sigmas. So you have the overlapping between the carbon sp2s, right? And each one does that. And there's a 1s hydrogen on each one of the carbons as well, right? So if you take a look at it from the side, you have to remember that even though you have 3 sigma bonds, there is a p orbital that is sticking up and above and below each one of those carbons. So what happens is they can interact. You have a pi bond happening at each set. But what happens is because they all have that p orbital there, the orbitals almost are able to create pi's with one another, like all of them. They don't stay only between 2 p orbitals because it's exactly the same distance away from the other side where there's also a p orbital. So what ends up happening, is the electrons that are in that half-filled p orbital to make the pi bond end up basically being shared between all of them. They're close enough to all of the p orbitals that they can essentially jump from one to the next. So that actually goes back to why we can represent it with a circle in the middle. That's representing the delocalized electrons. So that's how we refer to them. They're delocalized because they do not stay in one pi bond. They kind of jump from pi to pi. So it's like a cyclic formation. So this is a very stable structure. And you'll see when we go to do chemical reactions next week, they are not very reactive for that very reason.